But those are great questions. Honestly, I prefer live myself because I just want people to see the raw, real stuff.
Okay, got it. Okay.
That's yeah. I believe there's magic in the raw, actual stuff.
Cool. All right.
Yeah.
Well, we should be out now.
Great. So we have a lot to get through. First, I want to say that the private sale is taking up a lot of my time, as I knew it would if I ended up having to be engaged. But that said, it's going quite well. About an hour ago, we had an update on the private sale for those who are participating in the private sale. The private sale is because of my experiences with the crypto market and the crypto space. The private sale is limited to accredited investors who are comfortable with a fairly high bar minimum. That won't be the case when we go to the ICO with the Rev when we launch Mercury. But for now, I really need to know that the people who are engaged, this is not just a day trading kind of speculation, that they're in this for the long haul and they understand this is a long-term investment in which they want to participate. So that's why the shape is the way it is. The sale itself begins on the 28th of August and will run through the 18th of September. If there are any more details that people in this community want to know about it, feel free to ask. But that's kind of the bare bones of the sale. If you feel strongly about one thing or another, please don't hesitate to contact me or other community members, Ed, or we also have Steve Kiriaga and Greg Heist who are helping with the sale. So they're also good people to talk to. Okay, moving on from the private sale, unless people have questions right now, I would like to move directly into the financial forecasts. As a preamble for the financial forecasts, I want people to understand that these are our best guesses based upon our experience, both over years of working in software, but also our experience in the crypto space. And I want people to look at these forecasts with a critical eye. So people really should look at these and give us your best wisdom. Question our assumptions. Look at this, as if the planning for this was really important, and you wanted to make sure it succeeded. And so look at all of our forecasts from the perspective of how we could improve them. Because this is just our best guesses, and we really need the community wisdom applied to these to improve them, so that our planning process can get better and better. So with that, let me please turn the floor over to Lisa, who has been preparing these.
All right. Well, thank you, Greg. I'm going to start by sharing my screen. Can everybody see my screen, and is it showing something that says financial projection disclaimer?
I see document one word.
All right. Let me see if I can slide. I'm on two monitors, and that's all. Okay. I'm just going to go. Hang on.
Yeah, it's kind of annoying. You have multi-monitor.
Okay.
Yeah, go ahead.
Yeah. So I hope you can see this well enough. So this, I just am going to repeat just a little bit of what Greg said, or emphasize that these projections shouldn't be relied on in any sense. You should really read this financial disclaimer here. It is part of the forecast file now, and essentially says you shouldn't rely on these projections in any sense. They will change. They are estimates at best. So I won't dwell on that any longer, and I'll take you to this sheet. And let me see if I can close a couple things so it shows up better on here. Okay, hang on. I was really thinking I'd be on a better screen. Can you see that well enough, or should I go back to a larger view? Are folks there?
I would say it's
oh, sorry.
Yeah.
Okay. You want the larger view?
I think you're good. I think you're good.
Yeah.
Okay, thank you. All right, sorry. Okay, so this is the overview of the forecast that we've put together so far. It goes from this year really through 2020. And I'll just walk you through these line items and give you the thinking behind our assumptions. So we've got revenues forecasted for the co-op in terms of platform revenues, and then also membership dues. Also, if you come down to here, you'll see some of our thinking behind the platform revenues. So basically, platform revenues are transactions processed times the transaction fee, or here it's labeled revenue per transaction. And the thinking behind the growth in the transactions being processed by the platform begins with the assumption that the platform will kick off mid-2018, but then that there will be some modest growth at the beginning as people are bringing on applications, and there's a good chance that the initial applications will be simpler, like wallets and so forth. And then by the time we get to 2020, that there'll be some really cool and more complex and engaging applications coming onto the platform that will really drive both the number of daily active users and the number of transactions that are being processed by the platform. So you can see in 2018 that we've got 34 million. Everything's rounded to thousands here. So we've got 34 million transactions being forecasted on the platform for that first half year, and then by the end of 2020 we're at 22 billion transactions being processed. And during this period there's a forecast of really nice steady growth. Again, thinking about that as we bring on very engaging applications, we should see strong growth in transactions happening. On the transaction fee, the 0.3 cents here is really just an estimate that works for this forecast. It provides enough revenue to start covering expenses, and I just would remind everybody that the idea behind the co-op, right, is to bring as many transactions as possible onto the platform, and that will allow us to continually lower that transaction fee. So the 0.3 shouldn't be taken as this is it. It's just really a placeholder as we look at the transaction growth that is really happening on the platform. So if you multiply transactions processed by revenue per transaction, you will get the platform revenue number. Then the other part of revenue is the member dues, and that, I'm sure you all know, is $20 to be a member. And then the growth of membership, the assumption underneath that really is sort of the same idea as in transactions, and that is, initially there will be modest growth, probably a little more growth around when the platform first launches, but where we probably will start seeing a lot of growth is when there are a lot of applications and users on the platform, and they will want to become members. So that's the assumption behind the membership growth in that revenue number. So I'm just going to pause for a second and see if there is anybody that has a question about, or really a thought that they'd like to share on these revenue projections that we've started with. Okay, very good. I will press on. So we have operating expenses bucketed in 3 different groups. We've got R&D expenses, and that is the development staff, hosted services, really any resources that are going to be needed by the co-op to develop, maintain, and grow and maintain growth as users grow on the platform. You can see that for 2018 and 19, the amount of spend there is fairly flat and then starts to increase in 2020. And again, that represents that if we are expecting to have strong transaction growth, which we're showing in this forecast, then we'll need to obviously expand the development staff to support that user activity. On the sales and marketing bucket, you have your staff there, you've got advertising, you've got promotional expenses for the launch of the platform for an ICO, you've got budgeted an annual developer conference. And really, if you look at 2020, there's quite a bit of money budgeted just to say the co-op is going to have to spend money in some fashion just to drive developers to develop applications on the platform and to help them drive their users to those applications. And then the final bucket is G&A, or general and administrative expenses. And it's like your accounting expense, and then quite a bit of that is also legal and compliance expense. Given our business, we wanted to make sure that we really put in what we hope would be a robust number. But like everything in this forecast, we don't really have another business model to look at to give us a sense of where some of these expenses might come in. So everything is truly, a estimate. Then I just want to point out a couple of other lines here. So this, see if this clicks. So I don't know why it's not clicking. But anyways, that gain and loss on the sale of cryptocurrency, the 1.7 million in 2017, that represents really the amount of gain the co-op had related to the AMP redemption process. So it's a pretty good estimate. It was very successful. The next line is the member rebate or the patronage dividend. And there's a number out there in 2020, and that number really is a total swag. I really don't know how it's going to look, but we wanted to include something in the forecast so that people remember that part of being a co-op will be to provide some type of rebate or patronage dividend back to those members that are actively engaging on the platform. The next line is the private sale of rocks in the ICO. So we've got a minimum of 10 million we're hoping to raise through this private sale. Would love to do more, but would really like to hit that 10 million number. And then the ICO is set at 15. Again, that's an estimate that will change. I'm sure it will change. The timing could change. It could happen. It could not happen. But right now it's just a private sale. We're not calling it an ICO.
No,
I'm talking about the. I'm sorry, I wasn't clear. So the 10 million here is the private sale, and then the 15 here is a forecasted ICO.
Oh, got it. Understood. Thank you. Yes.
And that's strange, but anyway, the point of the 15 is that it is, there's nothing in the works. It's something that we wanted to put in the forecast, but that number could be, change. The number could change. The timing could change. The next line I won't dwell on. That's income taxes. I think we're all way too familiar with those. But I will bring you then down to the net income and the cash flow. So they're pretty much one and the same for the co-op. You'll see that in 2017 and 18, we're forecasting to have positive cash flow for the co-op in both those years. That's because we are forecasting to raise money through the private sale this year and then through an ICO next year, which will provide enough cash for the forecasted expenses that we have here in this plan. Then you'll look in 2019, you can see we're running a cash deficit here of about $5 million. And that means that really at this point in the forecast, there aren't enough transactions at the transaction fee to cover the costs, but the co-op in the forecast is, raised enough money that it can support the expenses that it wants to. And then you get to 2020 and transaction growth has come to a level that it's able to generate enough cash to cover its expenses, maybe provide a patronage dividend. So that's our thinking behind the co-op forecast. Again, everything is subject to change. It will be continually updated. So hopefully I have an opportunity to talk to you again about, what we're thinking about. And in some of the other worksheets in the file, you can see a breakdown of some of the items that we're budgeting for R&D, sales and marketing, G&A. We tried to budget really sort of the big items that people really could think about, but it would be very helpful for getting your feedback on, whether or not we're missing something there that we should be adding, or, we should be shaping that expense differently as the platform has more and more transactions being processed on it. So that's it. I don't know if you have any questions.
I had a question about the sales and marketing expenses in 2020. Just looking at the segmentation and just wondering why, if the expenses were for developer outreach, was it listed as a marketing expense as opposed to R&D?
Well, that's a really good question. And I think that it's sitting in sales and marketing because we just wanted something there that represented that if we expect to have, this type of transaction growth and daily active user growth, the co-op is going to, need to spend money. And you're right, that it could be that as we're getting to that point, the nature of those expenses really are more R&D related, because the development team is supporting other developers of applications. So thank you for making that point, that some of these estimates really could end up going from one group to another as we get a better idea of what that spend really represents. Does that make sense?
Yeah, I think it's also something to consider. I'm sorry, just really quickly, just from the perspective of an investor looking at financials, marketing expenses tend to be viewed as sunk costs, and so that there aren't any returns on those. And so it may behoove the co-op to classify them as developer expenses because there's an actual product being built and community engagement, as opposed to, marketing expenses, which sometimes can be looked at a bit negatively.
Oh, that's a great observation. I just wanted to amplify that a little bit. So one of the biggest spins is that we're creating a funnel that at the smallest end of this, we have bounties on bugs that are listed in Jira. So our bug tracking list will be open and available to the entire internet. And there'll be bounties on those. So people who want to participate by just grabbing a bug and fixing it can do that. But it goes outward from there. So people who have shown a kind of talent or proclivity or passion will be able to take on larger efforts, such as full feature development. And then out past that we are going to be encouraging, again, with Rock and Rev, the development of not just full features, but whole applications and other kinds of services that sit on top of the platform. And so a lot of that will be encouraged, but this also helps us create a path for people who want to get more and more engaged in the co-op, or who want to jump over and begin an incubated team underneath holdings. So that's so you're right that this is not just sunk cost. In fact, a lot of the cost turns into a return very quickly. As you may have seen, right? If a bug gets fixed, then that's greater value for the co-op. So it's new territory. It's a different way of organizing community engagement and community outreach that's enabled by the cryptocurrency capabilities. So I'm all ears for how to name this kind of thing.
Yeah. Now, this is Lisa. I think, whoever raised that point, that's an excellent point about, how I just wanted to build a concept, but, I probably have put it in the wrong bucket, and how that could be really not the right perception to be giving people. So I can see this changing already. So that's why it's a forecast and is subject to change. So thank you. That's a great point.
Yeah.
Yeah. It's Lawrence. From a sales and marketing standpoint, it will probably move that into more of an education bucket, because that's really what it is. It's about bringing the community together, as Greg pointed out, and we'll put it into something that's recognizable. We may recognize it, to the point to the person who made it, recognizable for an investor community. We want to be very on point with these. And Lisa, when I see you later today, we can take a look at this, and I'll make some suggestions for the different buckets.
Cool.
Okay, that's great.
Yeah, that was Kevin. By the way, Lawrence, that was Kevin Valentine who raised the question. Thank you, Kevin.
Thank you, Kevin.
Yeah, thank you.
Sure thing. No problem at all.
All right. Any other questions related to the financial forecast? I want people to be aware that we have a much more detailed staffing plan. And for those who are interested, DM me on Slack, and we can go over those in more detail. We've made some of that kind of information available, but again, we want people looking at our staffing plan with a critical eye, with respect to what it is the goals that we're trying to achieve, and giving us their feedback. This is really honestly a community effort. So we appreciate that. So that will help. And since the bulk of the spend part of this is in staffing, that will give you a really good idea of how the rolled up financials are reflected back into the work that we're doing. Likewise, you can cross. You can look at this against the work breakdown structure that we published some months ago, in terms of the 13 different internal milestones that we're hitting in order to get to Mercury. So people can see how the work breakdown structure correlates to staffing. So for example, there are 4 major areas that we're looking at. Right. So there's the Rchain development, including the compiler and other aspects of Rchain. There's the virtual machine development. There's the storage layer, and there's the COM layer. This may seem as a fifth component, but really it's the one that ties everything together, and that's the consensus capability. And so for each of those major components, we have roughly, if you break it down as 5 instead of 4, then we have 4 developers on each of those major components, with 1.5 of those devoted to integration with the other components, and DevOps and things like that. So DevOps is sprinkled throughout the team, so that everyone is, has someone on board who's thinking about how this gets packaged and how this gets deployed. So that gives you a kind of rough idea of how things are shaping up in terms of the more aggressive development, and how that relates to our spend. But we are wide open to other opinions and other ideas as people engage the material and see what our planning is and how things shape out. Okay, any other questions that people might have regarding the financials? Okay, very good. So moving on, we'll do some technical updates. Today, Mike and Tim and I had a good chat about the virtual machine. Mike and Tim and I are working on the re-implementation of the virtual machine in Scala. So we kind of walked through a little bit of the actor model background and how that related to the structure of contexts. So anyone who's opened the hood and looked at the C++ implementation of the virtual machine will have seen that the contexts represent, or the actor-based representation of the thread of control that goes from pulling a message out of the actor's mailbox and into, I'll just do a quick screen share and do a summary of what was, and then we recorded the session, and I'll make the link available to whoever asked for it. It's not edited in any way, shape, or form, but so whoever wants to see it, just DM me, and I'll give you the link for that material. So essentially, every actor has 4 components: an inbox, which is where it's receiving messages from other actors; a meta, which is a map from symbols to locations, and the extension is the map from locations to values. So this basically gives the actor's state. These two combine, and then the parent it can be seen as like a V table. It's a map from method or message types to methods. So this is what's used to dispatch from the message to some code. So essentially, a thread of control happens when the actor picks up the next message in the inbox. So that's going to look something like this. And it runs until the actor calls update. When the actor calls update, the control transfers to a new thread of control. Now this thread of control can still be active, but there's a fork between the state that this sees and the state that this sees. In other words, any updates to state or modifications to state here that occur after the update are not visible to this thread of control. That it's like they're in isolated worlds. And then the other thing that's important to understand with respect to this is that there's a difference between a message like this and a message like this. This is fire and forget. So the message happens and there's no expected return. So the return value of an expression like this is no intrinsic value, or abbreviated as NIV in Rosette. Whereas here, this behaves as if it were a function call. So the message is sent to the actor with these arguments packaged up. The actor receives the message, processes them, and is expected to return a value. And that value is what this expression results in. So as an example, in a let expression, if you say let V be the result of processing this, then V will be that value in the expression E. And in that sense, so if we were to compare the let to a couple of other overarching control structures, seek basically says that, first this will be processed and then the next will be processed in order. And if you have a seek with an update like this, then all of these messages will be processed with their values returned before you get to the update. You can view the let as giving you a means by which you could implement seek if you so desired, because this will be completely done before E takes place. And this is related to the context code in the sense that a message like this results in a context, and that context has an overarching context, which is, in this case, the seek expression. Right. So likewise, here's a message expression that will result in a value, and there's a context associated with it, so a thread of control. And that thread of control returns up into this thread of control. Now here, in a block expression, you have concurrency by default. So even though this returns up into this block, there's no guaranteed order here. And in fact, so you would have a race between handling these messages and the updates, the update to the actor state. So this would not necessarily be safe unless the programmer knew what they were doing. So Mike and Tim and I went over this structure in a little bit more detail, relating it to the C++ code, but largely to understand how the context actor corresponds to the concurrency in the Rosette virtual machine. Now, the other place where this is super important with respect to the Rchain semantics is that the context is the gadget that we use for our version of continuations, which allows us to implement the tuple space, which allows us to build out the semantics of Rchain. And that, if you go look at the compiler, the Rchain compiler, so roslang.scala, then you'll see exactly how that is utilized to provide those kinds of semantics. So the tuple space can be viewed as a kind of pipe fitting between the Rchain semantics and the actor semantics underneath. Over time, eventually, we will get rid of this semantics almost entirely, but that's going to have to line up with a better concurrency story as relates to the hardware. Essentially, what the Rosette VM is providing for us is a view of the hardware as if it were concurrent. Now, hardware is concurrent these days, but abstractions like LLVM don't give us a good concurrency story. It doesn't give us a good interface or API to take advantage of that concurrency. Certainly not one that is safe. So Rosette provides this kind of intermediate API that's concurrency aware, and then the Rchain semantics provides an even better, a more rich view of a concurrency aware kind of execution semantics. So that's essentially, in a nutshell, what Tim and Mike and I have been working on. And here's a little bit of context to see what we're the kind of thing that we're engaged in. Any questions about that? Yay, silence is golden. Actually, I really like it when people have questions.
I've always been looking into Rust, and which I guess runs on the LLVM, and it seems like the semantics there are fairly close to Rchain, and I'm wondering what your thoughts are on that.
Yeah, it's an interesting. It might be interesting to utilize Rust as another kind of target. We need to be in control of the target. So that's one of the reasons why we ended up not going with Rust or the Zinc machine or some other things, is because we need to have a little bit more fine degree of control. Otherwise, we have to kind of go to the Rust team with a request for changes that understandably would probably be ignored. But yeah, it is an interesting target for sure. Okay, any other questions on that before moving on? All right, so we'll move on. Mike and I have also been doing some fairly extensive work on the ladle algorithm. There was a nice development over the last couple of weeks where we're really fleshing out, how much model theory versus how much type, proof theoretic construction we can get away with in the calculations. Mike came up with some really nice examples that we looked at to kind of shake out some of those questions. It feels like we have a much better handle on how we're the way in which the distributive law plays in how do I say this? Mike, you want to help me out?
Yeah, so the problem is fundamentally that we want our types to be able to be written down. So they have to be finite length. But we want their meaning to be able to be infinite. We want to describe infinitely many programs with the same type. So what we had been thinking of as a distributive law is something slightly different. Because in a distributive law, you need to have the same set of ground terms on both sides. Whereas here we want a set of finite things, finite predicates or types on the left, and a set of potentially infinite sets on the right. And so we've been poking around at various categorical constructions that might shed some light on what exactly that needed to be.
Nicely said. Yes. Yeah. I actually have been really delighted by that conversation. And anyone who wants to go a little deeper, feel free to poke us, and we can easily set up some time to answer questions on that. And then another update. Joseph Denman and I have been working a lot on the cost model, and just kind of going over some of the desiderata with respect to the cost model. There's a long history of even in the pi calculus, there's a long history, and the pi calculus went through some fairly significant overhauls. And so understanding how all of those overhauls impact the cost model has been something that Joe and I have had to bootstrap our common understanding on. Joe, if you want to say a few words about that, feel free.
Sure. I actually have some kind of interesting stuff that I've been fleshing out since we last spoke.
Cool.
The problem we're trying to solve in a large sense, the overall idea is that we want the change in the amount of phlogiston that a program has available to it to reflect the energy, so to speak, required to cause P to go to P prime. Those familiar with the process algebras will know, that that's the energy required to cause a reduction. From a VM perspective, it's, to cause a VM to, change state. So Greg and I are kind of thinking now the place where we're at is, how can we encode the notion of cost directly into the row calculus? And this actually has, taken in the correct light, some pretty massive implications. So to kind of lay the groundwork for what I'm about to say, let's go ahead and admit a couple of things. The first thing that we should admit is that at runtime, the cost of something is the additive inverse to whatever phlogiston supplied, right? So if I have phlogiston, then I'm going to subtract the amount of phlogiston required to cause a system to transition. The second kind of larger thing to admit is that if rev is ultimately a conserved quantity, under that assumption, then phlogiston is as well, because we can kind of translate freely between the two. And then the third thing in this explanation is that if some amount of phlogiston goes from, say, pH to pH prime, then that implies that P can go to P prime. And that distinction is actually pretty important, because a P can go to, because saying that P goes to P prime implies that pH goes to P prime is very different than saying pH goes to P prime implies that P goes to P prime, because we need phlogiston to allow our system to transition. So here's kind of the overview of how we can look at it. So if we view, say, a process expression or our program as a P with a possible reduction. And
Joe, are you intending to share your screen?
No, I don't actually have any of this written down yet, but it's certainly worth doing in the future. So I'll hurry through. But essentially, if we view P from a physical standpoint as a closed system, initially, let's say cold, then we can view the phlogiston as energy entering P that actually causes P to heat. And once P is heated, we can allow it to reduce. So as our phlogiston goes to the reduced amount, our process may reduce. The reduction's triggered. And the interesting part is that from a thermodynamic sense, pH, or the phlogiston going to the smaller amount of phlogiston, can be viewed as heat, or as a hot bath going to a cold bath. And anybody that's kind of versed in thermodynamics knows that work is produced. Well, in our case, the work produced actually reflects the reduction that occurs, which we can represent as a difference in phlogiston, which represents cost. So by the first law of thermodynamics, our heat is accounted for as a positive value, that is the phlogiston entering, and our work is represented as a negative value, that is the cost of the reduction occurring. And the closest thing that I've actually found in the literature to this, as Greg and Mike know, is the stochastic version of the pi calculus. But no other system or no other interpretation of the pi calculus has ever really come close to being able to reproduce these kind of results, or even interpret any sort of thermodynamic implications directly, because no other system or no other calculus has had the need to introduce a conserved quantity such as our phlogiston besides us. So future work kind of says that we could go on to not only examining the row calculus in terms of its thermodynamic implications, but then to also check our model for the phlogiston pricing model against those, as well as the laws of the Rho calculus. And there are a bunch of papers that could actually come out of this sort of interpretation. So yeah, that's just a kind of I know this isn't very organized, but I was just kind of scribbling it out before the meet. So in the future, I'm sure I'll have a more put together presentation, but yeah, that's what I've been working on. Any questions?
That sounds really cool.
Yeah. Oh, and yeah, I forgot to say the funny part is actually that while I was going through all of this, I already told Mike, but while I was going through all of this and I was looking at the literature, I actually found Mike's thesis paper, which was pretty funny.
Yeah, it is. It's a great idea. I mean, just to put a little bit more flesh on this, essentially what we're looking at is generalizing a rule like this, which is the single step COM rule, which so on the one hand we want to talk about so there are three things we need to do. One, we need to give an upper bound on the cost of phlogiston. And to do that, what we do is we provide a function, which we think of as like, we write it as like the measure of. So that's the vertical bars around that. So it takes a row expression and produces a row expression decorated with a cost, right? And we're looking at a rule that works like this, where starting with a basic red X, which is a output rubbing up against input, you go and calculate the cost of the continuation, and you add in the cost of the continuation together with the binding and the synchronization costs. So that's the basic kind of rule, and then there's an assumption about that the type of X, which gives you information about the cost of transmission over X. And what Joe is pointing out is that kind of rule where you have some information about the cost of transmission over X is related to this idea of a rate of transmission through X, which is the overarching intuition in the stochastic interpretations of the pi calculus. And what we see is that the best presentations of the stochastic interpretations of the pi calculus are, and in particular the ones done by Cardelli and Mardare, are the presentation is limited to the label transition system of the pi calculus, which goes all the way back to the beginning of the pi calculus. And they're not expressed in terms of the reduction semantics. And so there's some very interesting technical results that come from shifting that presentation to a reduction style presentation. And having the kinds of insights and intuitions that Joe was talking about help with the navigation of some of the technical details, because when you have a kind of mental model that relates to a physical thing like heat transfer, it helps navigate some of the technical calculations.
That's true. That's all of that's certainly true. What I'm saying also, though, is that if we wanted to hash out, the Rho calculus in terms of a stochastic calculus which applied rates to a channel, yes, we could do that. But I think that because we've introduced this need for phlogiston in our system, we can actually model much more. Because, so the stochastic calculus assumes the mass action law, which is cool, right? That's how chemicals operate at equilibrium, but it can't go lower than that because it doesn't have the ability to actually directly model thermodynamic transfer. So what I'm saying is that yes, we could do that, but we can also go much further on kind of a much deeper level.
Yeah, exactly. So again, I guess part of the excitement here is that we have a bunch of practical problems to solve. So we have to have the estimate for phlogiston, which we need to give as guidance to a system or a developer that's about to deploy a contract. They need to know roughly how much rev to supply, and so we have to basically take the estimate of the contract in terms of the phlogiston, and then use the phlogiston to rev conversion, which is again set by the market, to give them an estimate for how much rev to supply to get their contract to go at least K steps. So that's one piece of the puzzle. The other piece of the puzzle that we have to provide is so the programmer doesn't, when they write contracts in Rholang, they're not writing the contract as if there's any awareness of phlogiston. So they're not in charge of updating the phlogiston. That we take their contract and rework it as a part of the compilation process into a contract that can make steps if there's phlogiston present. So the other part of the work that Joe and I are doing is to create that spec that says, given a contract, what's the variant of the contract that is resource constrained. So this is a source-to-source translation of the contract into a contract that is constrained, and that entails some interesting things in and of itself. At the detailed level, there are interesting problems there, because the phlogiston supplied is more or less centrally supplied to that contract, right? It's not central in the sense that there's an overarching entity that's watching all contracts, but there's a supply of phlogiston that's made available to that contract. But that contract may have many threads of activity, each of which are constrained by that common available supply of phlogiston. So there's a subtlety in making sure that each of the threads can go as far forward as they can with the existing supply of phlogiston. So
right. It essentially becomes a homogeneous resource allocation problem. And
yeah.
And what we're worried, or what we don't want to happen, is that one thread goes to execute or runs to termination and has additional phlogiston, while another thread is starved of phlogiston. We want to make sure that if there's any extra, that the threads which don't have it are given it, or that problem never arises. So yeah, yeah, right. So our ideas and how we prevent that is actually by tailoring our cost estimates, because our ability to allocate our phlogiston accurately and to eliminate phlogiston or the action of updating or of deducting phlogiston entirely from the contract becomes more accurate as our static cost analysis becomes accurate. Because ideally, we don't want the deduction mechanism to influence or actually it can't influence the execution order of our threads at all.
Yeah. I mean, I think it's going to do so a little bit. So anyway, so that's kind of an update on where we are. One of the key observations in all of this is that you can there are two ways to go around this. You can talk about an encoding, as a source-to-source encoding in the calculus, or you can talk about expanding the calculus with additional information and then showing that you can get rid of that via such an encoding. And you want to show that no matter which way you go around that, that sensible or reasonable approaches make both of those equivalent, and so that they end up being sanity checks for each other. All right, so you can either start with a calculus that's richer in the sense that it has either rate information or other kinds of or cost transmission information associated with channels, and then de-sugar that information in terms of an encoding in the calculus, or you have an encoding in the calculus and show that it would respect a de-sugaring process that has certain properties. So that's a nice little sort of sanity check that we've done the right thing if we express this as an expanded calculus. So a lot of work is going on, a lot of thinking is going on, and we're driving to the place where we'll have where again, the aim and the goal is that the spec of all the cost work feeds directly into the development process. And then and then relate it back to our discussion from before, when we were talking about the financial forecasts. So all of this work rolls up under the Rchain development piece that we talked about when I was talking about how the work breakdown structure rolls up into the financial forecast that Lisa led off our discussion with. So I want people always to be able to trace all of these discussions as detailed or as deep as they go back into line items on our schedule and line items on our budget, so that there's this clear traceability and clear accountability to the community. All right, so we went deep on that. We're coming up against the top of the hour here. I want to stop here and just ask if there's any community questions from the community. Anything that people want to ask about, or they're concerned about, or any cool stuff they've been working on.
Well, I had my demo for the storage layer today.
Yes, so go for it. We'll go over. I want to see that.
Okay, well, it takes 15 minutes. I mean, I just want to let you know. I mean, so if you want me to do it, I'm happy to.
Let's do it. Yeah, I'm an idiot. Just go for it. And also, Tim is going to do the fuzzer. So let's just do it. And if I have to jump off, you guys can stay on. But I want to see this.
Okay.
You should have interrupted me sooner.
Okay, I'm just sharing my screen now. Do you guys see basically a terminal window?
I do.
Okay, great. So here we go. So I'm working on the storage layer. It's also sometimes called the key value store. And what it is, it's the local database that will run on each Rchain mode. And just for the purposes of this demo, I'm going to refer to it as the store. So that's also, the storage layer, key value store. And from a very high level, it's just like any other database. You walk up to it with a key and you get back a value. In our case in particular, you have a key and it's associated with a list of blobs, where a blob can either be data or a row calculus continuation. The row calculus continuations are not in this demo, but they are to be done. The store has all your standard CRUD features: create, read, update, delete, and those are all pretty straightforward. So I'm not going to focus on those in the demo. Rather, what this demo will focus on is what's interesting, which is how you query our store, how you find keys that match what you want. And the basic, most general use case here is that you have a query, which is kind of like a key pattern. It's a description of a bunch of different keys that may match in the store. So you walk up to the store and with this query, and what you get back are all the keys in the store that match your query. If you're familiar with regular expressions with strings, that's analogous, where a regular expression is a pattern that will match multiple strings. In our case here, the matching of a query with keys in the store is modeled after the logic programming language Prolog and its unification process. And I'll kind of explain that as it comes up. Just a few words about the code. It's written in Scala. Its interface or its API is database neutral. In other words, whatever, we're going to have an industrial database under this, which will probably be Mongo or Lightning, but you can't tell when you look at the API. There's no commitment about database that is evident at that level. And that's something else on my to-do list, is to, again, hook this up to an industrial database. At this point, the memory, or the store itself just exists in memory. And so what my demo here is we're just going to run an interactive test harness. So you can think of the code I wrote as sitting in the test harness, and we've got this interpreter here to kind of make it do things. So the prompt is, inscrutable, but basically those are the 4 commands that we have. It's just to remind me. A is to add a row to the store. D is to display the contents of the store. Q is to query the store, and E is to exit the interpreter. So let's just start out and do some simple things. What's in the store now? Display. Nothing. We're starting with nothing. Let's take advantage of the fact that it's empty and launch a query which we expect to fail. And this also gives us a chance to start talking about what keys and queries look like. For our purposes, keys look like mathematical function calls. So this is like A of 1, where A would be a function and 1 is the argument. It's actually closer, if you know Prolog, to a Prolog predicate. But you may wonder, why do our keys look like this? Well, that's just what works best for our tasks. So we're querying whether the key A of 1 is in the store, and it makes sense it's not. So let's start populating it. And our first few examples are going to use employees, because that's something that's easy to think about. And the data associated with the keys are going to just be sort of pseudo JSON here. So what I'm saying is I want to add this row to the store where we have Alice is an employee, and Alice is like a name or a constant, as opposed to a variable, which we'll encounter later. And that key, employee Alice, maps to this JSON. So we get back, we add it, and we know it worked because we see the contents of the store, and we see that Alice is in there with the associated value. So let's do the obvious thing. Let's ask the store if Alice is there. So the fact that we got a row back like this indicates that key is found by the query. And it also introduced this notation here, which I understand is maybe a little bit hard to unpack at first. But we'll do successive examples that increase the complexity, and hopefully it'll make sense. The first thing to notice is that it's a list separated by a comma. There are basically 2 pieces here. There's the query vars piece and the key vars piece. And what we also want to note about these is that the curly braces in its case are empty. And what these empty braces mean is that we don't have to make any changes to match the query to the key in the store. And that makes sense because our query, which is this, matches exactly what's there. So what this kind of cumbersome or inscrutable notation means is that we don't have to make any changes for the match. So just kind of continuing to do what's natural here. Let's do a query about Bob. Is Bob an employee? It makes sense he's not. So let's hire Bob. So Bob's in as well. So this gives us the opportunity to ask more interesting questions. Let's do a query where we introduce a variable. Variables start with capital letters. So you can kind of see what we're asking here is tell me all the keys that are employees that match the variable X. The fact that we get 2 lines here indicates that there are 2 different keys in the store that match. And you can see that we've gotten more detail here in the results. And so what what this says right here is if you start with the query, which is employee with the variable X, if you start with that and replace the variable X with Alice, that will take you to the key in the store. And the Bob example works analogously. So yeah, so we're introducing the idea of a variable here, and this is an example of a very simple example of prolog unification, where you've kind of got this pattern and you're asking for all the things in the store that can match it. Okay, so let's do a different example here just to increase the complexity a little bit. So what's interesting here is that we're introducing a row with the key mortal of X, where X is a variable. So that's what's new in this little wrinkle here, is everything we have in the store so far is all about constants. Alice is an employee, Bob is an employee, but now we're putting in a variable into the store. And you can see for the data, I'm just starting to use, just a placeholder, because the data is not important for any of this example. So everything that we're interested in is about the interaction between queries and keys. So I'm just kind of dropping the JSON pretense because the data is just pretty much irrelevant. Okay, so we see that got added. And so let's just do some kind of natural queries that come up here. Alice, because doesn't start with a capital, it's not a variable, it's a constant. So we're asking, is Alice mortal? Does this query, mortal Alice, match any key in the store? And it turns out it does. And we get to see a new development here in our notation. This time, the query vars is empty, but the key vars part is populated. And what this says is that if you start with the key of X, with the variable X, and substitute Alice, you get the query. Or you can think about it going the other direction. If you take the Alice in the query and replace it with the X, you get back to the key in the store. And the reason that there are these two different pieces to our output is because there are two different kinds of unifications that can happen, either where you make changes to the query to get to what's in the key in the store. Other times, the way the unification happens is that you start with the key in the store and you make changes to it to get to the query. So let's just I don't know. Let's ask this question then, where we're at our query has a variable in it as well, and you get kind of what we'd expect. We recognize this from the first query we did, or one of the first queries, where you don't have to make any changes to match query with the variable X to the key. So one natural modification that suggests itself is to ask with a different variable. And what the output we get here indicates that there are two ways to get there. You can either change the query, where you replace Y with X to get the key, or you can start with the key and replace X to get the query Y. And all right, so we want to now increase the complexity of our examples. And for this, we're leaving behind sort of human comprehensible domains of employees and mortals. To sort of talk about the greater complexity, we need to just kind of start dealing with predicates and functions and stuff. So my next example just demonstrates the nested properties of unification of queries and keys. So here we've just got a function A that takes a function B of A. So we're adding this row to the store. And yeah, it appears right up here. So let's just see a few examples of how the nested stuff works. So we're asking about that, and it's there. No changes are required. So let's do a query where we include a variable here. So we're asking all keys in the store that match this variable X. And we get a response, which is something what we'd expect. You start with the query, you replace the X with 1 to get what's in the store. Okay. And we'll just, to make sure that things are as we expect, we do a query that shows that that's not there. Now let's add we're to just increase the complexity here, we're now adding a key that has a variable in it. So we've got those two in there, and both of these in here now. And so we can ask a question like, this is our query, what does it match? And the one way we can make our query match what's in the store is to take this X and replace it with a 2. Let's just do a few more examples that suggest themselves here. This says that there are 2 ways that you can match this query to 2 different keys in the store. One is to do nothing, or the other is to change the key, or to replace the 1 in the key with an X to get back to the store.
This is great, Griff. This is
Okay.
really this is the kind of thing. This is the kind of thing that we really wanted to see. Did you have a specific thing that you wanted to drive to?
I'm just a little bit more complexity here. Let's just do one more case. Let's just do one. This is just to give you a taste of, you know, what's more real world examples might look like, or where things are more complicated. And so we can just ask a few quick questions like, so D is very complicated. If you break it down, it takes 2 arguments, and the first argument is very complicated, but we can just ask a general question like this: what values A and B would match the value that we have, the key that we have in the store, and you kind of get what you'd expect here. Yeah, I guess I can just leave it there then, and that's maybe one more comment. Just this is be the end of the actual interactive part of the demo. What's next to do is to hook up a database and do performance tests, and to add continuations. So those are the next items on the to-do list. So that's the end of my prepared part of my presentation, and I'm open to any questions you'd like to ask.
Well, first of all, thank you so much. This is really, really cool, and I hope other people really kind of get the sense in which this is pretty awesome. I do want to make a couple of comments. These aren't questions so much as comments, so that people can see this in context.
Okay.
So first of all, what this does is it when we go to store the state of the VM, for example, we will be using this API to store the state of the VM, and that's how locally things will get stored. and then and also how things will get retrieved. You can basically compare this if you're looking for comparisons to Ethereum. This is similar to their Tri-E or Tree or Tri database. But here, our keys are much more sophisticated, and the matching algorithm for determining when you have a match is more sophisticated. But it turns out that if you can flatten out all of your keys just to simple, just constants like strings, then this should, from a performance perspective, match or be better than what we see with the Tri database structure. The other, so that's what's happening at the base level. Now, there are two other comments with respect to the base level. One is that notice that there's not necessarily a relationship between what the key is a key for and the structure of the key. So in Griff's examples, there's no relationship between the value, the structure of the value, and the key. And so so any query is only going to be on the structure of the key, and unless someone knows what the kind of relationships are maintained between the keys and the values, any information or insight into the structure of the key gives you almost no information about the structure of the values. And we see this as a security feature. In particular, if you make there be some kind of relationship, and in particular homomorphism between the key and the value, then your queries on keys turn into queries on values. But that's now entirely up to the application that's using the data store. The application is deciding what the relationship is between the key and the value, and that can be made as hard computationally as someone would want to guess the relationship. So you could still have a relatively straightforward relationships between the keys and the values, but it'd be very, very hard to guess computationally what those relationships are. And we see that as a security feature of this data store. And then I can talk more about that, but people should be aware that that's what's going on. Now, the other side of this is that we replicate this structure once we have the Casper stuff in place. So this is the basis for the content delivery network. This very same Prolog style semantics can be utilized to provide a very rich content delivery semantics for applications that are sitting on top of the Rchain network. In particular, if you think of if you think of the keys as names or channels, and you think of those as either pointing to continuations or to data, that gives us the means by which we can interpret the Rchain constructs. So we get a higher level Rchain construct, but it also mediates between Rchain, which is decidedly point to point, and broadcast mechanisms. So when a key has a variable in it, or when a query has a variable in it, as Griff pointed out, you can get multiple different answers to queries. So by placing data, attempting to place data into a situation, or read data from a situation where you have a key with a variable in it, or you have a query with a variable in it, you can get multiple answers back, and that ends up being the way to provide broadcast style mechanisms in this framework. So So again, it just like the rest of the Rchain network, there's a two-level structure. So there's a low-level version of Rolang that doesn't know anything about blockchains. And then on top of that, we write Casper contracts. And that provides a notion of what consensus is and the attendant notion of a blockchain. And then on top of that, we have a semantics that provides the smart contracting mechanism. And then above that, we reiterate the kinds of functionality that Griff provided, so that we then have this very rich content delivery capability, right? So now you can query blockchains, you can query applications. So blockchain explorers are almost trivial. Blockchain explorers are almost trivial in the in this setup, and there are many other applications that can utilize this semantics to do rich query and content delivery style applications in this framework. So I know that probably wasn't the clearest explanation. We've given many other explanations of this in the context of Special K. So that's where a lot of this work derives from. Griff, did you have any other comments you wanted to make around this?
No.
Awesome. So Tim, if you're available, let's get that fuzzer demo.
Sure. So for the Rosette rewrite, we want to generate parsers to different languages, namely Haskell, Java, OCaml, and Python. And to do that, we currently use both the Antler tool and the BNFC tool. And for that, we want to make sure that all generated parsers basically eat the same input and deny the same input, so that they're basically working in the same way. And one way to help with that, to make that sure, is to test these parsers against fuzzer data. So that's why I wrote a fuzzer. Let me share my screen. Can you see my screen? Anyone? Hello?
Yeah, we see it.
Okay. So this is the Scala project, which is generating the fuzzer output. Basically, I encoded the whole BNF of our parsers into case classes. You see that here. And once for valid output and once for invalid output. And so basically you can just go to an SBT console in this project and generate terms. For example, you do like 100 invalid terms like this, and then it should be here. So now you have like 100 lines of invalid RBL code, and the same goes for valid output. Yes, and you can also change the breadth and the depth. And when you have these outputs, you can test them against the different parsers. So here we'll just quickly walk through the different passes with the output generated with the fuzzer output. So this would be the valid fuzzer output against the Java parser generated by Antler. And here we see it completely eats the fuzzer output, the valid fuzzer output. When we do the same for the invalid fuzzer output, we can see that it fails. Mismatched input, yada yada. Same. Same for the Haskell parser. This is the Haskell parser generated by BNFC. Once with the valid fuzzer output, where you can see that it completely eats it, parser successful. And once with the invalid fuzzer output, and you can see that we get errors. And it's basically the same for the Python parser and the OCaml parser. And what this tells us that so far it seems like they're actually working in the same way, which is good for us. Yeah. Yeah, that's my demo.
Great. That is really, really good. Thank you for taking this on and getting this done. This is fantastic. One of the advantages of working in this way is that we're trying to make it as easy as possible for those people who want to make language bindings for the Rchain semantics, right? So we're probably not going to go out of the gate in the Mercury timeframe with a production-ready Python implementation. There may be some toys and some prototypes, but there won't. We have no plans currently to make a production-ready Python implementation. But that doesn't mean that another group can't take it on to provide a Python binding for all of this. And these kinds of capabilities that Tim is demonstrating make it a lot easier to do that. And we'll make it we'll provide mechanisms to make it as easy as possible, so that everyone is deriving their implementations from the same executable specs, which will guarantee a level of interoperability amongst the implementations and traceability and correctness amongst the different implementations that currently we don't see in blockchain space. And this is just the very beginning of this kind of approach, and I'm just super impressed, Tim. This is really awesome. Actually, both Griff and Tim, these are great demos, and it just makes me really happy to see this kind of work underway.
Thank you.
No, thank you. Cool. Well, we're like 30 minutes over, and I was supposed to be on a call with Joseph 30 minutes ago. So thank you, Joseph, for your patience. I'm going to jump off, but feel free, guys, to keep chatting if you want to. And thanks again to Christian for his work, being there every week to record these things. It's really amazing.
No problem, guys. Next week.
All right. Ciao, ciao.
Thank you.
Bye.